the two random variables here. And we have seen the examples how it can be taken here. We have seen those examples and some properties, that is fx of minus infinity will be equal to 0, that is an event here. And even these two properties, which are it is for the single random variable, the same concept is applicable for here also here. And we have seen the bivariate, the derivative of the CDF, which is called as a PDF, you are going to call here. So that's what we obtained here. And we have seen the properties of the term also we have seen here. Okay, so like the area under the curve, it is considered as the area under the volume, and some more properties we have seen for the joint PDF here. And also we can able to obtain the single PDF from the joint PDF. So we are going to call that one as the marginal PDF. So you are going to call here. Okay, so you can take the definition for the marginal PDF. Okay, you can take the definition of the marginal PDF. Okay, when the probability density function, fx of x and fy of y, when the probability density function fx of x and fy of y, can be obtained from the joint random variable. You can take a bivariate random variable, fxy, you can take fxy of x comma y, then such a PDFs are called, marginal PDFs. Then such a PDFs are called as the marginal PDFs, or marginal probability density function you go to call here. Marginal probability density function you go to call here. Okay. So done. So in the last class we are done up to this one here. Now let us continue from this one here. So we have some more like we defined for the single random variable. We defined the mean, variance, covariance. Okay, mean, variance, standard, that is standard deviation, and the mean square value we defined here. Similar way we are going to define for that one. So before that one, let us see some more concept here. Okay, so independent events we can take here. Independent. Okay, so this is nothing but the independent events we are going to call here. So in the beginning we have seen the definition of the independent events we have seen here. Independent events. Okay, so you know that the two events are said to be independent events if it does not, the occurrence of one event does not depends on the occurrence of the other event. You are going to call that as the independent events. You are going to call a statistical independent event. You are going to call here. Okay, so if the occurrence of the one event does not depends on the occurrence of the other event here. Okay, occurrence of the one event does not depends on the occurrence of the other event, then we are going to call that one as a statistically independent event. You are going to call here. Correct? No, we defined in the beginning of the module 1 here. And one more is which is called as a mutual exclusive events here. So mutual exclusive events is the thing, but the two events cannot occur at a time. You are going to call that one as a mutual exclusive event. You are going to call here. The example of that one is the thing, but human eyes are the ears here. Okay, we can't see at the two different directions at a time here. Okay, the other one is statistically independent events. Statistical independent events is nothing but the occurrence of the one event does not depend on the occurrence of the other event. You are going to call that one as the statistical independent events. You are going to call here. So for the statistical independent events, we have seen that the probability of A intersection B is equal to the, so the probability of A into the probability of B will be there here. Okay, so the probability of A intersection B will be equal to the probability of A into probability of B will be there. So the same concept you are going to apply for the joint, the bivariate CDF. You are going to apply the same concept you are going to apply here. Okay, so the same concepts you are going to apply, same concepts you are going to apply for the joint PDF, or we can say that the joint, sorry, bivariate CDF. You are going to apply the same concept you will apply here. Okay, you can take if the random variable x and y, if the random variable x and y are independent random variables, then okay, if the random variable x and y are the independent random variables, then so we can define the CDF can be defined like this here. So the CDF is, it is the probability of we have okay, so first we are going to write, I'm going to write the generalized form here. So that is probability of x can take the value less than x here. Intersection of y can take the value less than or equal to y here. So this can be written for the for independent. For the independent, we can write this one like this here: fx y of fx y of x comma y. So by applying this concept here, so wherever the intersection is there, we can write as a product. We can write here. So that is probability of x is less than or equal to the x here into the probability of y is less than or equal to the y. So this in turn we know that. So this is nothing but the fx of x here. Okay, the individual probability into the fy of y we can write here. So for the statistical independent events, the bivariate CDF is equal to the product of the individual CDFs will be there here. Product of the individual CDFs here. Okay, so this is for the statistical independent random variables here. Okay, so done, right? Okay, so similarly we can extend this concept for the bivariate PDF also we can extend here. So similarly for bivariate PDF, similarly we can extend for the bivariate PDF. So PDF is nothing but it's a derivative of the cumulative distribution function. So it is given by d by dx of d by dx of fxy of x comma y, d by d square, dy here. So this can be written as, so because since we know that fxy is equal to fx of x into fy of y, so we can write this one as a d by dx of fx of x here into d by dy of fy of y. So this is nothing but fx of x here, because the derivative of the CDF is nothing but PDF here, fy of y here. So this is for the statistically independent random variables. We can have the PDF as the product of the individual random variables we can take here. So done, right? So this is called as the independence we are going to call, or for the independent random variables, we can use this concept here. Done. Okay. So this is for the statistically independent random variables. Okay. So far we have seen the concept of the bivariate. So far we have seen the concept of the CDF. We have seen that is for the bivariate CDF. So for the multiple random variables, we have seen the proper CDF. Its properties we have seen here. PDF and its properties we have seen here, and we have seen the independent events we have seen here. Okay, next let us see the multiple random variables here. Multiple random variables. Okay, let us see that one. Afterwards, we'll go for the expectation of the joint random variables we'll see here. Okay, so done, right? Okay, so taking the next one. So next one is called as a. So far we have seen the concept of the CDF for the two random variables we have seen here. One is called x and y, and even the PDF also for the two random variables x and y we have seen here. Now I'm going to extend the same concept for the multiple random variables. I'm going to extend here. Multiple random variables means x, y. It will be something like x1, x2, xn up to the xn will be there. Up to xn will be there. So we'll see that one as a multiple random variables we'll call here. So that one you're going to call it as a multivariate density functions we'll call here. Okay. So it is called as a. Take the next concept as. So multivariate density functions. Multivariate density functions. Okay, so you can take. So multivariate is nothing but, suppose if the number of random variables more than 2, you're going to call that as a multivariate random variables you're going to call here. So for that one, we are going to define the CDF and the PDF you're going to define here. Okay, you can take if the number of random variables is more than 2, then it is called as, if the number of random variables is more than 2, then it is called as multivariate random variable. Multivariate random variable. Multivariate random variable. Full stop. Okay. So you can take the CDF of multivariate random variable is given by the CDF of the multivariate random variable is given by. So how we return the CDF for the bivariate random variable, we can extend for the multivariate random variable like this here. So it is x1, x2 up to the xn. So a number of random variables will be there. So here x1, okay. So small x1, okay. x2, x3 up to the xn will be there. So this can be taken as it is a probability that the x1 can take the value less than or equal to the small x1 here. Okay, so intersection of, sorry, x here, not x1, intersection of x can take the value less than or equal to the x2. So intersection of like that up to the, so this is nothing but the intersection symbol here. So x can take the value less than or equal to the xn here. Okay, so like this we can define the multivariate cumulative density function. We can define like this here, multivariate cumulative density function here. Okay, done. Okay, so similar way we can obtain the PDF, that is the CDF. The CDF is nothing but cumulative density function. Sorry, cumulative distribution function. PDF is nothing but the probability density function. We can obtain by differentiating this one here. So you can take the PDF of multivariate random variable. The PDF of the multivariate random variable is given by, so the PDF will be denoted like this. So fx1, x2, x3 up to the xn, okay, of small x1 comma x2 comma x3 up to the xn. So this can be obtained by differentiating. So how many times we need to differentiate? N number of random variables will be there. So with respect to the n number of random variables, we need to differentiate here. So dx1, dx2 up to the dxn. Okay. So what we need to differentiate is, we need to differentiate the multivariate CDF. We need to differentiate here. So up to the xn of these quantities. So x1, x2, x1 comma x2 comma up to the xn here. So if you're going to differentiate that one, you're going to get the PDF, the multivariate PDF you're going to obtain from the multivariate CDF you are going to obtain here. Okay. Done, right? Okay. So similar way, we have seen one of the property of the CDF we have seen here, that is CDF and PDF here. So you can obtain the CDF from the integrating the PDF here. By integrating the PDF, we can obtain the CDF here. So you can take CDF can be obtained by obtained by integrating the PDF given by. So if you are going to integrate the PDF here, you are going to get that one here. So this is fx1, x2, x comma n here. So x1 comma x2 up to the xn. So this can be integrated from where to where we need to do it. Integrate is, so from minus infinity to the x1, integral from minus infinity to the x2. So like that, integral from minus infinity to the xn. So what we need to do integrate is, we need to integrate the PDF we need to integrate. So it is fx1, x2 comma up to the xn of x1 comma x2 comma so on up to the xn here with respect to the dx1, dx2 and so on up to the dxn here. Dxn. Okay, so dxn we are going to integrate here. Okay, here we can take x also, we can take here others u1, u2, u3 also we can take here, no problem here. u1, u2 up to the un we can take here. So right, this is the integration here that can be obtained. The CDF can be obtained from the integrating the PDF here. Okay, so similar way we have seen one of the property of the PDF that, so the area under the PDF, the volume under the PDF is equal to 1 year. So for a single random variable we have taken the area, for the multiple bivariate random variable we have taken the volume here. Okay, since because two random variables will be there, so the intersection will be volume you are going to call here. And when now the multiple random variables is there, we can take the volume we can consider here. So you can take the volume under this PDF should be equal to the 1 should be there here. So that's another property we have seen here. So we can take that one. So these are the different formulas we have seen here. So take this one. The volume under multivariate PDF is equal to 1 year. Is equal to 1 because the volume, whatever the volume will be, that is under this will be equal to 1. So that is the integral. If you're going to integrate from the minus infinity to plus infinity, how many times? So how many random variables will there? So many times we need to integrate here. If here are n is there, so we need to integrate the n times here. up to the xn of x1, x2 up to the xn. So with respect to the dx1, dx2 up to the dxn here. So this is equal to the 1 year. This is equal to the 1 year. Okay. So this is the area, the volume under the PDF is equal to the volume under the PDF is equal to the 1 we'll get here. Done, right? Okay, fine. Now okay, so this is for the multivariate random variable. Yeah. So next we'll see the concept of the mean covariance and some factors you're going to see. Like we are seeing for the mean variance, the mean square value like that. We'll see for this one also here. So that one you're going to call it as a bivariate expectations you're going to call here. So we are going to take the expectation of that one you're going to take here. So bivariate expectations we will consider here. So any doubts? So we have seen the concept of so far. The CDF we have seen. This one we have seen. Independent we have seen. Multiple random variables you again seen. So next one is expectations we are going to see here. Expectations is nothing but it's a mean variance covariance like that we are going to see here. So right, bivariate expectations. Done. Okay, so you can take the expectation of the bivariate random function of the bivariate random variable is given by so we can apply the expectation for the even for the this bivariate random variable also. I'm going to consider this as a function of two random variables you have considered here. So expectation of g of x comma y. So this will be equal to the, so you know expectation is nothing but it is the integral of x of x into fx of x into dx here. So since two random variables are there, so since this is a function, I can take this as the gx of y. So I'm going to consider g is a function of two random variables here. We know what is the difference between the x and the g of x here. Okay, already we are seeing in the first model we are seeing. Okay, so right, I think you have remembered that one. So fxy of x comma y into dx into dy here. So this is for the expectation for the two random variables here, which has been considered. Okay, so g of x comma y is a function of two random variables x and y here. Function of two random variables x and y. So you can take away g of x comma y is a g of x comma y is an arbitrary function. Is an arbitrary function of bivariate random variable. Bivariate random variable. Okay. Done. Okay, take. Next, let us take here. Suppose you have the g of x comma y is a. So here g of x comma y is a, it's a function of two random variables here. Suppose if I'm going to consider g of x comma y is a function of single random variable. Okay, if g of x comma y you can take is a function of single random variable. Is a function of single random variable. Okay, if I'm going to consider it's a function of single random variable, that is we can consider this is a function of the g of x. If I consider here, let me see what will happen for the this expectation here. Okay, so getting the concept here, no? So here I have taken the function of the two random variables we have taken here. Suppose if the g of x is a function of a single random variable, let us see what will happen here. So I'm going to substitute. We are going to find out the expectation of this one here. Expectation of g of x will be equal to the, so here g of x comma y is a, so this will become g of x, it will become here, so minus infinity plus infinity, so this will become okay, so here sorry, I have forgotten here because dx dy is a, so here two integral signs is there here you can take, because we are going to integrate with two random variables, no, two integral sign is there, one is for x, another is for the y here. Okay, now g of x comma y, we are going to take it as a function of the single random variable. So we had made the correction this one, no? Fine. Okay, so one integral is a function of x, other integral is a function of y here. So since I'm taking the g of x here, So I'm going to write this one is a function of the one integral, which is a function of x here. Next, other one is a function of the other two integrals, that is fxy of x comma y, okay, into dx into dy here. Dx into dy we can write here, dx into dy, done. Dx into dy we are written here. So right now we know that integral of minus infinity plus infinity fxy of x comma y into, so this dx belongs to this integral here. So now dy belongs to this one here. So from the marginal PDFs, okay, so we know that, so from the marginal PDF, just I see in the again the example of that is sorry statement of the marginal PDFs I given here. So from the marginal PDFs we can write integral from minus infinity to plus infinity fxy of x comma y into dy can be written as it's a fx of x we can write here, fx of x here, that is from the marginal PDFs we can write here. So if I'm going to substitute here, so we'll get the expectation of the g of x, which is same as the single random variable expectation you're going to get here, that is fx of x into dx will get here. So this is how we can obtain the mean of the single random variable from this bivariate random variable. By using the marginal PDFs we can obtain like this here. Okay, done. So this is the expectations you are going to call here of the random function here. Now in the previous single random variable we have seen that the expectation of the x we are going to call it as the expectation of the x we are going to call it as a mean we are going to call here, mean you are going to call. So similarly, if the two random variables are the x and y, we can't call this as a mean, we can't call it here. So we are going to give some other name you are going to give for this one, because it's a two random variables are there. So we have to give some other name. That one you are going to call it as a correlation you are going to call here. Correlation we are going to call here. So that is called as a correlation between the random variables x and y here. So you can take, okay, take the next one. The correlation between the correlation between the correlation between the random variables x and y, random variables x and y, the correlation between the random variable x and y is the expectation of their products. I can take it, expectation of the, you can take it as the expectation of the product of the, you can take, this is a better sentence, expectation of the product of the random variable x and y. The correlation between the random variable x and y is the expectation of the product of the random variable x and y here. Okay, this is a better sentence, I guess. Okay, so expectation of the product of the random variable x and y. So that is a limit. You are going to call this one as the expectation of x and y. Okay, so we know that the expectation of x and y is nothing but, so that is integral whenever x and y will be, so x and y, so we have the joint or the bivariate CDF will be having, okay, so into dx into dy here, dx into dy. So this is the called as the correlation we are going to call here, the correlation of the random variable x and y we are going to call here. Okay. Okay, so usually this correlation is used with zero mean bivariate random variables. We are going to use this correlation. You are going to use here. So you can take usually the correlation is applicable for the zero mean bivariate random variables. Is applicable for the zero mean bivariate random variables. Okay. So similarly, this is for the continuous random variable here, continuous bivariate random variable. So similarly, we can applicable for the discrete also we can apply here. So discrete for this one, we can take it as the average here. Okay. So you can take similarly for the discrete random variable. Okay. So you can take the expectation is nothing but it's averaging here. expectation is nothing but the averaging. So it is taken as averaging. So 1 by ni into summation. So this is the ni. I can take the 1 to the n here, 1 to the n. So xi into yi here, xi into yi. Okay, xi into yi. Suppose, okay, so there are some three cases are there here. Suppose if the 1 by ni, that is summation I is equal to 1, xi into yi is greater than 0. Suppose if this one is greater than 0, then you are going to call as a positive correlation. You are going to call here. Then you are going to call that one as a positive correlation. You are going to call here positive correlation. We are going to call this one as a positive correlation. Similarly, if the summation ni, summation I is equal to 1 to n xi into yi, okay, so is less than 0. If it is less than 0, we are going to call that one as a negative correlation. You are going to call here negative correlation. Okay. Similarly, if this is equal to 0, so this is the first case, second case, and the third case. If ni summation I is equal to 1 to n xi into yi is equal to 0, then we are going to say it's a uncorrelated. We are going to carry here. You're going to call this one as a uncorrelated. Uncorrelated, we are going to call here. Okay. Uncorrelated, we are going to call here. So this is the correlation you're going to call here. It is similar to what we have seen in the case of the mean of the random variable we've seen. So, but now you're going to call this one as the correlation you're going to call here. Okay. So next one is called as the covariance. Let us see here. Covariance. So we have seen the variance we have seen here. Variance we have seen. Okay, that's it's the difference between the random variable x and its mean here. So similarly, we are going to see the covariance here. Okay, covariance you're going to see here. So you can take the covariance of the. You're getting the definitions right. Getting the definition. So okay, similar way let's take here the covariance of the covariance of the random variable x and y is given by x and y is given by. So covariance will be defined as a covariance COV we are going to use here x comma y. So this is nothing but it's expectation of the x minus nu x, okay, into y minus nu y here. X minus nu x into y minus nu y. Okay. So x minus nu x into y minus nu y here. So let us expand the RHS part here. So by multiplying taking the product of this one here. So x into y it will become xy here. Next x into this one become okay minus x into nu y minus nu x into y minus into minus will become nu x into nu y will get here. Now we know that the expectation is a linear operator. We can applicable for the single one here. So it will become expectation of xy minus. So nu y, the expectation of the constant is the constant only. The expectation of x is nothing but it will become nu x here. Expectation of x is nu x. I'm writing straight away because you know that one. Okay, so plus nu x into nu y will get here. So this one will get cancelled with this one. So we can call this as the covariance is the. Okay, so the remaining term is this one. So this is the covariance of x comma y. Sorry, covariance of xy here. Within the square bracket you are going to write here. So it is nothing but it's a correlation here. The correlation of the random variable x and y and the difference of their means here, product of their means here. So this one we can define as the covariance here. Done. Okay, so done right. So this is a covariance here. Suppose for the random variable x and y, bivariate random x and y, if any of the mean is equal to 0, then the covariance will be equal to the correlation here. The covariance will be equal to the correlation. So this is nothing but the correlation. This is nothing but the covariance here. So you can take, suppose if okay, if nu x or nu y is equal to 0, if any of the nu is equal to 0, then if any of the mean is equal to 0, so we can take this one as covariance of x comma y will be equal to it's a correlation here. Okay, the covariance will be equal to the correlation you're going to get here. So right. So in the exam they will ask you the what is the define the terms covariance, correlation. Okay. So many times they'll go to ask here. Okay, so you can write these things you can write here. So done, right? Okay. Okay, we'll see the next one here, next concept here. So next one is nothing but uncorrelation here or uncorrelated x and y here. Uncorrelated x and y here, x and y. So uncorrelated is nothing but there we can call it as a statistically independent events we can call here. Uncorrelated is nothing but the statistically independent event here. So for the uncorrelated that one, so we are seeing that for the beginning we are seeing that is the independence we are seeing here. So for the statistically independent events, so the occurrence event does not depend on the other event here. The probability of A intersection B will be equal to the probability of A into probability of B will be there here. So that one you're going to call it as the uncorrelated. You're going to call the same concept is applicable for the this one here. Okay, so you can say it here. If the okay, if the random variable x and y, you can take if the random variable bivariate random variable you can use here. The bivariate random variable x and y, the bivariate random variable x and y are uncorrelated, then so if it is these two are uncorrelated, then we can say that the covariance of x comma y will be equal to the 0 will be there here. The covariance of x comma y will be equal to 0. Okay, the covariance of x comma y will be equal to 0 will be there. So how this will be equal to 0, we'll see that one here. So we have seen that I told that probability of A intersection B will be equal to the probability of A into probability of B here. So this is for the independent events or uncorrelated events you're going to call here. So similar way we have that one here, right? So we have, so what we have is the expectation of the x and y is there. So for the uncorrelated random variables, we can write this one as the expectation of x into the expectation of y we can write here. Expectation of x into expectation of y. So this is called as the new x here, and this is called as the new y here, new y. Okay. So what we have the formula for the covariance here, the covariance of x comma y. So this is nothing but the expectation of xy minus new x into new y is there. So the expectation of xy is nothing but, so it is called as the new x into new y minus new x into new y. So this will become equal to 0. So this is for the statistically independent events or uncorrelated events. The covariance will be equal to 0 will be there here. Okay, done, right? So this is for the uncorrelated random variables x and y are the statistically random independent random variables here. So done, right? Any doubts? Okay. Now next let us take the orthogonal random variables we take here. Orthogonal is the thing, but they are perpendicular to each other here. Perpendicular to each other means they are having the phase shift of 90 degree will be there here. So usually you are going to consider the orthogonal signals you are going to consider here. I think in your mathematics you have come across the Gram-Schmidt orthogonalization procedure you have come across, right, in your mathematics. So that procedure we are going to use in order to model the transmitter, in order to model the how the signal can be transmitted in terms of the carrier wave. We are going to use that orthogonal signals you are going to use here. So when you come to the sixth semester in the digital communication, you're going to study that concept here. Orthogonal is nothing but they're perpendicular to each other here. Suppose if I'm going to consider this is a sine signal, so this will be the cos signal you're going to get here. So these two are nothing but the orthogonal signals here. Okay, orthogonal signals, that is nothing but the orthogonal random variables we'll see here. Okay, so for the if x and y are the orthogonal random variables, so you can take if the x and y are the orthogonal random variables, then if x and y are the orthogonal random variables, then expected value of the xy is equal to 0. Expected value of the xy is equal to 0. That is, the correlation will be equal to 0 will be there here. Correlation will be equal to the 0 will be there here. Okay. That is, correlation is equal to 0. Correlation is equal to 0 will be there. So right. So if this correlation is equal to 0, then the covariance will become equal to the, so 0 minus this one here. So you can take then covariance of x comma y. So this will become equal to the minus nu x into nu y will get here. Minus nu x into nu y will get here. Okay. Then, so this is the uncorrelated and orthogonal here. So similarly, we can extend the uncorrelated concept can be extended for the nth random variable we can extend here. So that one you can call it as the independent we can call here independent. Okay, so you can take that one. So independent x and y. Independent x and y. You can take here. If the random variable x and y are the if the random bivariate you can take here. If the bivariate random variable x and y, bivariate random variable x and y are uncorrelated, then uncorrelated with the case we can take here with the case of independent of x and y, with the case of independent of x and y, independent of x and y, then so you can define the expected value of the nth moment you can call here. So this will be, it is nothing but integral from minus infinity to plus infinity. So here, so x to the power of n into y to the power of n we are going to consider, because already we have seen the nth moment here in the single random variable. So fxy of, sorry, so this one is fxy of x comma y into dx into dy, Okay, so for the independent random variables, we can write fxy of x comma y can be written as fx into fxy here. So we can extend like this here. So minus infinity to plus infinity integral x to the power of n into y to the power of n into. So for the independent, we can write this was the fx of x into fy of y. Already we have seen this one here. So into dx into dy, So this can be written as, let us separate the integrals here. So minus infinity to plus infinity x to the power of n into fx of x into dx integral y to the power of n into fy of y into dy. Okay, so this is nothing but the expectation of the nth moment you are going to call here, okay, into expectation of the y to the power of n. So this is the same concept it has been extended here. So what are the same concept we have seen for the uncorrelated random variables? So this concept has been extended for the nth moment, it has been extended here. That's it here, nothing else. Okay. Done, right? Okay, fine. So this is nothing but the independent here. So next we are going to see one more factor which is called the correlation coefficient. You are going to see here correlation coefficient. Okay, so you can take correlated.
Yes, sir.
Yeah. Any doubts? Okay, so these are the definitions we are seeing here. So later after the IA, I'm going to take. Okay, fine. So after the IA, I'm going to take the problems I'll take after the IA, I'll take here. Okay, so you can take correlated x and y. Okay, so we are going to define the correlation coefficient. You are going to define here. That one is called as the, okay, you can take the correlation coefficient. The correlation coefficient of the bivariate random variable. The correlation coefficient. The correlation coefficient of the bivariate random variable. Bivariate random variable x and y. X and y is given by. So this will be called as a rho. You are going to call here. This symbol, you know, it is a rho here, RHO rho. So right. So it is nothing but it's a covariance of x and y divided by the the standard product of the standard deviation sigma x and sigma y here. Covariance of x and y divided by the standard deviation, the sigma x into sigma y here. Sigma x into sigma y. Done. Okay, so this is the covariance will be defined here. Similarly, for the transformed random variables, suppose okay, done right. So this is called as the correlation coefficient you are going to call here. Okay, so this is having certain no properties, right? Okay, so take a next line. Take let y is equal to ax plus b, ax plus b, y is equal to ax plus b. Okay, so this is a transformed random variable here. Is a transformed random variable. Is the transformed random variable. Transformed random variable. So then, okay, so we'll define the covariance of this one. Let us define here. Then covariance of x comma y. So the covariance of x comma y. So we know that the covariance of x comma y is nothing but its expectation of the x minus nu x into y minus nu y. X minus nu x into y minus nu y. But we have y is equal to the ax plus b. Okay. So but x is equal to y is equal to the ax plus b here. Let us substitute this one in this expression here. Let us substitute that here in the expression here. So it will become the covariance of x comma y will become equal to the expectation of x minus nu x into, in place of y we can write as ax plus b minus nu y will get here. Ax plus b minus, okay, ax plus b minus nu y. So a similar way we can write the mean expectation of the y can also be written as a into nu x plus b. We can write no expectation of this one by the, we already see in the module 1 here. So just I'm going to write that one here. So minus a into nu x minus into plus will become minus only b will get here. The expectation of y can be write like this here instead of writing in the second steps. One more step here. Okay. So right, we can write like this one. So let us do simplify here. Expectation of x minus nu x. Okay, x minus nu x here. Let us simplify this one. Ax plus b minus a into nu x minus b is there. I rewriting here. So plus b minus b will get cancelled. A is the common here. So you can take expectation of the x minus nu x. Let us take a common here. So it is the x minus nu x will get here. So you know by applying the linear operator, a can be taken outside here. So a into expectation of, okay, so x minus nu x the whole square. X minus nu x the whole square. So that is nothing but covariance of x comma y. X minus nu x the whole square is nothing but we know this is nothing but the variance here. So sigma x square here. Already from the module 1 we have seen this is nothing but the variance. So it is nothing but the sigma x square will get here. Okay. So sigma x square you are going to call. So this is the covariance of the transformed random variables we have seen here. So right. Any doubts? Okay. So you have seen the so far we have seen the many concepts you have seen here. Just to be recalled, I have taken the bivariate expectation you have seen here, the expectation of the sum function of the random variable. Next we have seen how we can obtain, and the expectation of the two random variables you are going to call it as a correlation. You are going to call here correlation, and for the similarly for the discrete random variable we are going to take it as the average. You are going to take if it is greater than 0, it's a positive, negative, and the uncorrelated you are going to take here. Next, the covariance of random variable explains the thing with the it has been considered like this here. Okay, so if the x and y that is we have seen the covariance here, we got this one. Suppose if the any one of the mean is equal to 0, then the covariance and correlation are the same here. And uncorrelated is the independent random variables. We have seen this concept here, and orthogonal also we have seen the concept here, and we have seen the concept for the independent random variables for the nth moment you have considered. So this is the nth moment here, and for the uncorrelated random variables we have seen the transformation also we have seen here.